All right, our next video in our series about gases, we're going to talk about our final law, and then we're going to kind of combine everything all together. So if you remember correctly, all the problems that we've done up until now have always talked about this term, a fixed quantity of a gas. And when we say that term fixed quantity, what we've been talking about is we're talking about that the fact that the amount of the gas has not changed. And a lot of times when you think about a gas, you're like, well, the amount doesn't matter. Well, it makes a big impact. Think about the propane tank in your yard. That propane obviously can run out. And so the amount of gas is pretty important. And sometimes that amount of gas can change. And that's where Avogadro's law comes into play. So today we're going to learn how to describe the relationship between the volume of a gas and the number of moles of that gas. And then we're going to learn about what's called the ideal gas equation. So there was a French guy by the name of Joseph Guy Lussac, and he flew what are called lighter than air balloons, or hot air balloons, to an altitude of about 23,000 feet. And this is quite a while ago. Even nowadays, going up that high, you're usually in an airplane. So this guy was quite the adventurer. And what he said is he said that he observed this law called the law of combining volumes, and that at a given pressure and a temperature, the volumes of gases that react with each other are in ratios of these small whole numbers. And what we know now is we know that Avogadro, which is the guy that came up with Avogadro's number, the 6.02 times 10 to the 23rd, is that the volume of a gas, again, now we've got a constant temperature and pressure, is directly proportional to the number of moles of that gas. So we kind of learn about this with volume and temperature, that if the volume goes up, it's because the temperature went up, or vice versa. Here, if the volume of the gas goes up, it's because we've added more gas to the system. If the temperature doesn't change and the pressure doesn't change, the only thing that can make the volume of the gas go up is by adding more gas to it. The way that we measure that is we measure that in moles. Now, this is going to seem kind of strange, but the letter N is the letter that we use for moles. I guess they figured that they had used M for too many other things, so they used the letter N. And so what it's saying right here is that the volume is directly proportional to the moles, which means, again, if you add more moles of the gas, you are going to increase the volume of the gas as well. Now, here's something that we can see here. This is a pretty important page here. Number one, going back to Avogadro, here's his number right here. This number is 6.02 times 10 to the 23rd. We know that is equal to 1 mole. It doesn't say it there, but we know that that's what a mole is equal to. Just like if this said 12 instead of 6.02 times 10 to the 23rd, we would know that that 12 means 1 dozen. So we have 1 mole of gas in each of these containers. There's 3 different gases, helium, nitrogen, and methane. And you'll notice that at the same temperature and the same pressure, they all occupy the same volume. And we're going to talk about how we come up with that number here in just a little bit. So, but using this information from Avogadro's law, we can determine that 1 mole of, and it says a gas, what I would say there is I would say 1 mole of any gas occupies 22.4 liters when the pressure is 1 atmosphere and when the temperature is 0 degrees Celsius. And 1 atmosphere of pressure and a temperature of 0, as we know, is called standard temperature and pressure, or what we call STP. You should be familiar with that term by now, but if not, that is what STP stands for. It is the standard temperature, 0 degrees Celsius, just like how we see here, and the standard pressure is 1 atmosphere of pressure. So anytime you have any gas at standard temperature and pressure, it will have a volume of 22.4 liters. And that is known as the molar volume of a gas. Now, What all of this leads to is basically our final law. So Boyle's law, as we know, is the relationship between volume and pressure. When one goes up, the other goes down. Charles' law tells us about volume and temperature, and Avogadro's law tells us about volume and moles. Now, if we combine all three of them together, obviously the commonality that they have is they all have volume in them. And so what we get is we get this right here, where the volume is proportional to the temperature times the moles divided by the pressure. Or what we can say is if we move this volume down to the bottom, the temperature times the number of moles over the volume times the pressure is equal to a constant. Now, in all of the other ones, we've created an equation where we didn't end up using a constant. But in this instance, we're going to actually have to formulate a constant. And remember, a constant is something that never changes. So when we figure out this constant, it's a number that you're going to need to know, and it's a number that doesn't change. So how do we figure that out? First of all, we have to give it a letter. So the letter that they give it is the letter R. So you've got pressure and volume on top. You've got N and T on the bottom. And what we're going to try to solve for is we're going to get this letter R. So the way that we determine this constant, this letter R, is by using the standard temperature and pressure, which is 273 Kelvin, 1 atmosphere of pressure. And also we know that 1 mole occupies 22.4 liters. So when we put all of those into our equation right here, it actually comes out to be 0.08206. So sometimes you'll see it with going out 5 decimal places. Sometimes you'll see me write it as 0.0821. But really, you should always go at least a 0.082. Any of these are also perfectly fine, but that one is also acceptable. So notice that we've got the pressure and the volume, and then we've also got our moles and our Kelvin on the bottom. So notice that our number, the value for R, and again, this is a constant, okay? It never changes. It's always 0.082 or 0.0821, depending on how far you want to go out decimal-wise. And notice the units. It's not liters minus atmospheres. It's actually liters times atmospheres. So sometimes the way I write it, I'll write 0.0821, and then I just write L ATM over Kelvin mole. And so sometimes you'll see it without those. The dashes are in there just to separate them a little bit so it doesn't look like you're writing a capital L with ATM together. So that is a number that never ever changes. Now, let's rearrange this equation here a little bit. And this is our big one right here. If you remember anything from our whole gas section, this is the equation to remember. This equation is called the ideal gas equation. And it's simply said as the pressure of the gas times the volume of the gas is equal to the moles of the gas times that constant times the temperature gives us our equation. Now, you'll notice here that in our R value, we have liters, atmospheres, and we have Kelvin, and we have mole. In the past, I've always told you, that your temperature must be in Kelvin. Okay, but now we've got more stipulations. When you have a pressure and you are using the ideal gas equation, what unit must your pressure be in? Atmospheres. When you have a volume, what must your volume be in? It must be in liters. Now, well, the mole part, well, duh, it's always going to be in moles. Remember that very commonly, when we measure things, we don't actually measure the moles, we measure the grams. So sometimes you'll get the mass of a gas, and you're going to have to convert the grams of that of those particles of gas to the moles of the gas. So remember that also has to be in moles. So if you're given grams, make sure that you convert those grams to moles. All right, so let's take a look at an example of this. It says carbon dioxide gas is collected in a 250 milliliter flask. The gas has a pressure of 1.3 atmospheres and a temperature of 31 degrees. How many moles of carbon dioxide are there? So our first thing here is to take our equation, PV equals nRT, and let's solve it for what they're asking us for. The question is moles. So before I even begin, I want to take my equation here and I want to get moles by itself. Remember that the letter N is moles. So if I divide both sides by R and T, I'm going to get this equation. N is equal to PV over RT. So now this is an equation where we simply plug the numbers in and we'll get our answer. So first of all, our pressure. Our pressure is in atmospheres. So N is equal to 1.3 atmospheres times our volume. The volume, is in milliliters here. So we want that in liters. So when we convert milliliters to liters, remember we talked about this in a couple videos ago where you can move the decimal point 3 spaces to the left. And so 250 milliliters is just 0.250 liters divided by R, so 0.0821 liters atmospheres over Kelvin mole. And our temperature, which is in Celsius, take that away, 273 plus 31 is 304 Kelvin. Now, if we've done this correctly, we should be left with moles. Let's see if that actually happens. Now, before we go any farther, let me explain this. We've got a fraction right here, and we've got another fraction in our units in the denominator of that fraction. When that happens, let me give you an example. If you have 8 divided by 2/5, you might think, well, that's a difficult problem. It's actually not, but it's really similar to this. Imagine this is our 8 on top here, and this is our 2/5 right here for our units. What you do to solve this problem really easily is you take that 5 and you move it up to the top. And so 8 divided by 2/5 is really the same as 8 times 5 divided by 2, which is fairly simple in that it's 40 divided by 2 is 20. Okay, now for our case, we're going to do something similar. We can take that Kelvin mole, and we don't necessarily have to do this, but we should understand that really this Kelvin mole actually goes right up here on the top. And so when we're canceling things, we're going to have atmospheres over atmospheres, liters over liters, Kelvin on the bottom. And remember, this Kelvin is up on top, so that cancels. And guess what else is on top? What they're asking us for, which is moles. So the great thing about this equation is if you set it up correctly, everything will cancel except for what they're asking you for. So now we can go 1.3 times 0.250 divided by 0.0821. And again, if you just put 0.082, it's fine. This is just something that I'm used to throwing that 1 on the end. So, and then divide again by 304. And I get my number of moles equal to 0.013, 2 significant digits. 0.013, and obviously my units is moles. Okay, and that is the ideal gas equation. That's just a pretty simple, straightforward problem dealing with PV equals nRT. That's like I told you, that's a really common equation. You're going to see that a lot when you're dealing with gases. Okay, let's look at another example. It says tennis balls contain nitrogen gas to maintain their pressure. If a tennis ball has a volume of 144 milliliters and contains 0.33 grams of nitrogen gas, what is the pressure inside the ball at 24 degrees Celsius? So, first of all, they're asking us for the pressure. And this is, now we're kind of getting to that point where you have to start to think, what equation do I use? And I can see where it can be very, very confusing. If you think about it, oops, let's come back here. If we think about it, we've got a multitude of equations. We've got Boyle's law. We've got Charles' law. We've got the combined gas law. Okay, we've really got Avogadro's law, which involves volume and moles. We didn't actually look at this one, but it is a law as well. Also, remember, if volume is constant, then we can have this P1 over T1 equals P2 over T2. Oh, and guess what? Now we also have PV equals nRT. Okay, one easy way to determine when do you use the ideal gas equation is you'll notice that nothing is changing. It's not talking about how the volume was this and now it's something else. The temperature was this, now it's something else. Okay, notice that nothing is changing from one side to the other, that everything is staying the same, which basically means all of these other equations are out, because in all of them there's always one thing that's going to change to something else. So that's a good indicator for you that in this case we're just going to use the ideal gas equation. So PV equals nRT. So the pressure of the gas is actually what they're asking us about. So that's the one we want to get by itself. So right away the pressure is equal to nRT over V. So let's find out each of these things. Now, first thing first, moles. They don't give us moles. They give us temperature, they give us volume, and they give us grams. I don't see moles there. But now, again, now we're kind of going back to our first unit this second semester. We learned about how to convert grams to moles. So first thing we're going to do is we're going to take our 0.33 grams of N2, and we're going to go 28 grams in 1 mole of N2. And then you'll see our grams are going to cancel. And I'm going to take my 0.33. I'm going to divide by 28, which again obviously is the molar mass of N2 from the periodic table. And I get 0.012 moles of N2, rounding that to the correct number of significant figures. So I've got 0.012, that's my moles, 0.012 moles, times R, never changes, 0.0821 liters atmospheres over Kelvin mole. My temperature, 24 degrees plus 273 is 297 Kelvin. And then my final is our volume. The volume is in milliliters. I want to get that into liters, so 0.144 liters by moving the decimal point 3 spaces to the left. Okay, now let's check and make sure we've set it up correctly. If we have, everything will cancel except for our units for pressure. So moles on the top, moles on the bottom there in our fraction, liters on the top, liters on the bottom, Kelvin on the top, Kelvin on the bottom. All we have left is atmospheres, which means that we've set it up correctly. So now to do the math part, I'm going to go 0.012 times 0.0821 times 297, divide that by 0.144, and I get a pressure equal to, all total, to, let's see, I'm checking my significant figures here. This one only had 2, so I'm going to say 20 with a decimal point atmospheres. The calculator answer I got is about 20.3, so I've got to round that back down to 20, so I only have my 2 significant figures. So my answer, my correct answer after doing all of that is 20 atmospheres of pressure. All right, here's another one. 4.25 grams of helium gas at STP has what volume? Now, there's actually a couple of ways to do this one. Looks like we got another example after this. So, first of all, let's look at one way to do this. So what we've learned is we've learned that PV equals nRT. So PV nRT. This question is asking us for the volume. So volume equals nRT over P. So our number of moles, again, we've got this same problem where we've got grams, but we need to have it in moles. So a shorter way to do this might be to just go 4.25 divided by molar mass of helium is 4. So that gets us our moles. And then R, I'm going to run out of room, so I'm not going to write all my units in here. And then the temperature is the standard temperature, which is 273 Kelvin. And then our pressure, again, is the standard pressure, which is 1. So using PV equals nRT, I'm just solving for volume using the information that they give us. Remember that the standard temperature and pressure always is that 273 in 1 atmosphere. So I'm going to go 4.25 divided by 4 to get me my moles times 0.0821 times 273 divided by 1 gives me a volume equal to 23.8 liters. The only digit that I have is this one, and that has 3, so I'm also going to use 3. Now, that's one way to solve this problem. That's perfectly fine. No issues there at all. Another way to do this is to remember that when you're at STP, 1 mole of a gas at STP is always equal, I told you this at the beginning, to 22.4 liters. So if we take our 4.25 divided by 4, gives us an answer of 1.0625. I'm not worried about significant figures here. That is our number of moles. Well, we know that 1 mole is 22.4 liters. But in this case, we actually don't have 1 mole. We have 1.0625 moles. And so all you have to do in this case is really take your conversion factor here and say 1 mole 22.4 liters, and then your moles cancel, and hey, what do you know? I'm going to go ahead and do it on my calculator here. 1.0625 times 22.4 gives us our exact same answer, 23.8 liters. I don't care how you do it. I'm trying to show you both ways. Both ways are valid. Obviously, once you get used to this bottom one, this one's much quicker. But really, you have to be at STP for this to work. If you're not at standard temperature and pressure, this does not apply. You have to be at STP. All right, one more. What mass of hydrogen chloride gas has a pressure of 874, temperature of 52.3 in a 2.34 liter container? So let's take a look here at this one. They want to know the mass. Now, when we think about PV equals nRT, there's nothing about mass in there. And so we've got a problem here. But we do know that previously we have converted grams to moles. So then technically we could convert moles back to grams. So in this case, if we can get our moles, then we can convert our moles to our grams using the molar mass of hydrogen chloride gas. So that's what we're going to do, is we're going to find moles. So we're going to divide by both sides by RT. So N equals PV over RT. So our pressure here is in torr. Can't be in torr, it has to be in atmospheres. So I'm going to go 874, hopefully this is real familiar to you now, divide by 760, times the volume is already in liters, 2.34 liters. Sorry, my handwriting's so terrible. We're going to divide by R, so 0.0821. Again, I'm kind of slacking here on my units just because I don't have a lot of room. And then my temperature, 52.3 plus 273 equals 325.3. And I hope we set it up right because I don't have units to cancel, which is very wrong of me. So I'm going to go 874 divided by 760. Then I'm going to multiply by 2.34. And then I'm going to divide by 0.0821 divided by 325.3 equals 0.10, looks like three significant figures, 1 moles of HCl. Okay? And now that we have that, now we can say 0.101 moles of HCl. Now again, they want the mass. So now we need to go to the periodic table. Hydrogen has a mass of 1. Chlorine is 35.5. So altogether, that's 36.5 grams in 1 mole. Moles cancel. So that number times 36.5 equals 3.68 grams of HCl. And that is our last step. Okay, so these are some good introductory problems to the ideal gas equation. We will see more. They will become a little bit more complicated once we involve some stoichiometry in them. But this is a good introduction to the ideal gas equation. Okay, here's just some questions for you to consider as we go throughout this. But hopefully, if you followed along with these problems, you shouldn't have a problem doing these.